Good afternoon, everybody. I'm Maria Zuber, one of the PCAST co-chairs, and I'd like to welcome everybody, welcome the PCAST members and our general public viewers back from our break. I should note that we had no public comments for the public comment session, and so that will permit us to move right into our next session. I would like to remind everyone that this meeting is being live streamed to the public and it's being recorded. The recording of this session will be available by next week on the PCAST website. So as Francis mentioned earlier this morning, PCAST is considering the future of research. And in this session, we hope to address some of the many factors that are affecting the research enterprise. And we've chosen to do so through the lens of the work of several exciting and impactful researchers. There are significant new factors that are impacting research today, including higher salaries of grad students and postdocs, which, by the way, are much deserved, higher lab materials costs and equipment costs due to inflation and supply chain challenges, increasing compliance demand due to nefarious foreign influences, and the ubiquity of AI. All of these are examples. Now, some of these are positive, such as the growth of AI. Some of them are not so positive, but all of these drive up the cost and complexity of doing research, while federal funding has been flat or declining, with unfortunately no relief in sight. We've also increased recognition of the value and opportunities associated with interdisciplinary research, but there are limited paths to publish or support such research projects. However, despite these challenges, there are researchers who are successfully navigating exciting paths. And we are going to hear from 3 of those researchers today. Okay, I'm going to introduce the speakers for our session. But I note that longer biographical information is available online on the PCAST website and in the members' briefing books. So today we have with us William Anderegg of the University of Utah. He studies the future of ecosystems, specifically how drought and climate change affect forest ecosystems, including species interactions, carbon cycling, nature-based climate solutions, and biosphere-atmosphere feedback. After that, we have Marina Vance of the University of Colorado Boulder. Marina specializes in environmental engineering with a focus on nanotechnology and the dynamics and impacts of particulate matter on ambient and indoor air quality. Finally, we have Mionat Bell from Johns Hopkins University. She engineers and deploys innovative biomedical imaging systems that simultaneously address unmet clinical needs and significantly improves the standards of patient care. So I'm going to ask each of you to speak for no longer than 7 minutes. And after that time, we will have lots of opportunity for questions and discussions with the PCAST members. So William, you can take it away.
Well, hello, everyone, and thank you for the invitation to join you today. I'm excited to tell you about our research and some of the work going on at the Wilkes Center for Climate Science and Policy at the University of Utah. Next slide, please. Earth's forests provide tremendous benefits to society and currently dramatically slow the pace of climate change. They take up about 1/4 of the carbon that humans put up into the atmosphere every year. One of the fundamental challenges in the field is, will they continue to do so over the 21st century? Right now, we simply don't know. There is enormous uncertainty into what the future of Earth's forests looks like. Next slide. Earth's forests are really perched on a knife edge between two opposing sets of forces. On one hand, the benefits of rising CO2 in the atmosphere can help plants do more photosynthesis, grow more, and potentially maintain or expand the carbon sink over the 21st century. But on the other hand, the stresses of climate change like temperature, drought, wildfires, and pests and pathogens can overwhelm the benefits of CO2, drive forests to die off en masse, and emit carbon to the atmosphere, flipping the Earth's ecosystems and forests from a carbon sink to a carbon source. When and where each of these mechanisms dominate, we don't really understand. Next slide. Our work is really focused on a multi-scale understanding the physiology from a tissue to a cellular to tissue to organismal level of how plants respond to water stress, CO2, and other climate drivers. We then use a wide variety of approaches to scale that up to ecosystems, understanding how species interact and how resources are competed for and partitioned. And then finally, a much newer piece of our research is trying to bring this cutting-edge physiology and ecology understanding to inform decision-making around forests as nature-based climate solutions. And I want to tell you just a quick vignette of that work today. Next slide. Of course, the motivation here is that forests could potentially play a modest role in helping us tackle climate change. And there's this broad set of strategies that are termed nature-based climate solutions. Next two animation points, please. There's immense interest in this because obviously forests provide these co-benefits, but also there's huge interest in both the public and private sector in trying to leverage these as part of net zero commitments. The potential is maybe sort of 10 to 15% of the potential greenhouse gas emissions reductions or carbon removal that we need. So it has to be paired with urgent fossil fuel emissions reductions. Next slide. To do this effectively, though, forests have to do four key things. First, forests have to have a net cooling effect on the climate, which means that the carbon storage benefits exceed the other biophysical feedbacks like changes in albedo. Second, we have to these activities and investments have to lead to additional carbon storage and climate benefit than what would have occurred otherwise. Third, we have to account for the shifting of activities outside of project boundaries or jurisdictions. And fourth, we have to be able to understand, quantify, and account for the risks of climate change and the risks of people and human management decisions to durability. So things like wildfires and droughts. Next animation. I want to highlight, actually, thank you. Right now, there's a broad body of research that's documented. There are currently really large problems in existing carbon markets and existing carbon offset protocols in each of these four areas. And this is a really crucial research frontier at the science policy nexus. Next slide. Some of the work we've been doing is really trying to quantify and build maps and tools and projections of climate risks in US forests and global forests. These are statistical models we built of wildfire on the top. And these are based on satellite data of wildfires and then using long-term ground plot data for climate stress like drought in the middle and insect-driven tree mortality in the bottom. What you can see is we used high-resolution downscaled climate models over the 21st century across 3 different climate scenarios. And wildfires are projected to rise dramatically in the Western US, particularly in high emission scenarios. We see drought and climate stress rising substantially in the Southwest, and insect-driven tree mortality rising, particularly along the West Coast. Next slide. We can then take this along with other modeling techniques like mechanistic models in our Earth system models and get all the way to carbon and ask really fundamental questions of, is the future of US forests likely to gain carbon or to lose carbon? And we find large differences across these major approaches where you see generally in the upper left carbon gain in our system models where the effects of CO2 are really quite large. And then carbon losses in these prominent conservation tools like climate niche models in the lower left. The most realistic is really probably this upper right where you see carbon losses in the west and carbon gains in the northeast and northwest. Next slide. This has enormous policy implications because you can see these are California's current offset projects. Will you click the animation, please? And in our analysis in this most robust model, about 36% of the area of these projects is projected to lose carbon, even in a modest emission scenario. And that's dramatically higher than the insurance policies that these protocols have. Next slide. Finally, we're doing this at global scales as well, looking at the average risk percentiles across a huge range of different products. Next animation. And something I'm very excited about is leveraging just ongoing work with satellite and ground plot data to develop US and global reversal risks and buffer pool sizes directly needed for policies. Final slide, please. To wrap up, I think interdisciplinary funding from government agencies and foundations has been really instrumental to the work that I've done, and a critical role for risk-taking and blue sky thinking funding. I've been very fortunate and grateful to have a Packard Foundation fellowship to really launch this new nature-based climate solutions work that I shared with you. Next animation. Carving out the time for deep thinking and creativity is crucial, and all forces are pushing against that. And I certainly have experienced, and many colleagues have, the increasing compliance and administrative burden and costs of research as key challenges. Last point, and then I'll wrap. Here, as in many other spaces like AI, open science is fundamental, and there's a large risk of much of this being developed in the private sector, which I think would hamper some of our confidence, transparency, and accountability. Final slide. Thank you. Thank you very much.
Great. Thank you very much, William, both for the excellent presentation and for setting such a good example of keeping into the allotted time. So next, we're going to move on to Marina. I think you're up next.
Hi, everyone. While my slides get loaded up, I just want to first thank you for the invitation. It's an exceptional honor to speak to you all today.
I'm sorry, Marina, we seem to be having a little slide problem. So as soon as that gets fixed, we'll move on.
If it's easier, I can share my own screen. Do you think that's better?
That might be a good idea. We don't seem to be seeing your slides.
Okay. Okay, I'll race you. Let's see who gets this done faster.
That's the wrong presentation, right?
How about that? Can you see my
Looks
slides?
good.
Yeah, it looks great. Looks
Okay, let's see if I can get this to work. I have a single screen today, so sorry. Sorry about the delay. So today I'm going to talk to you about indoor fine particulate matter, known as PM 2.5 or aerosols. In my field, these terms are used interchangeably. And the reason I am very passionate about, and I'm dedicating my career really to understanding fine particulate matter, is to me very clear. The inhalation of particulate matter shortens people's lives, simply put. It's responsible for millions of deaths worldwide. The studies change every year. That number changes, goes up and down, but it's always in the millions. It's always a very large number. But beyond deaths, inhalation of fine particulate matter has also been related to what I like to call quality of life issues. Things like brain aging, anxiety, depression. Kids' test scores are lower if their schools are located closer to highways, for example. So these are obviously very important reasons to understand fine particulate matter. Now, if you look at this figure here, what you see is and there are many studies showing the same. This is just one of them. What you see is a dose response curve in 6 cities in the United States, and it shows a clear relationship between the concentration of fine particulate matter going up and the number of deaths going up. But one thing that's really important to note, and that many people don't realize, is that while these particles were measured outdoors in regulatory monitoring stations, these people were actually all indoors. So to me, that's a big knowledge gap, and it makes this curve not perfectly accurate, and I'll tell you why. And the reason is that people spend a majority of their time indoors. So this pie chart here came from a study that's over 20 years old. It was very, very important to get cited all the time. It should be updated because I'm sure things in our culture and society have changed a little bit over the past 4 or 5 years. But these numbers, if anything, have just increased. People spending almost 90% of their time indoors. That was the case already 20 years ago. And then the lion's share of that time, about 70%, is in their own homes. So given that, there's a continued need, in my opinion, to understand the chemistry and the physics of indoor environments and their quality and indoor chemistry. So I already talked about how people spend a majority of their time indoors, but also our buildings are becoming more and more airtight. This is great for energy consumption. It lowers our penetration of outdoor air pollutants, but it can be challenging because it might increase exposure to some indoor sources. So understanding the indoor environment becomes more and more important. Moreover, indoor processes are likely to differ from outdoor processes. So we have different sources. We are also at closer proximity to those sources. So particles and other air pollutants don't have that much time to react and change. So those timescales, those short timescales become really important to study. We also have different surfaces, much more surfaces indoors. So the interplay between surfaces and air becomes very, very important indoors. And we also have different oxidants that are driving the chemistry. Outdoors, we have the sun and photochemistry doing a lot of the atmospheric chemistry. But indoors, we have cleaning products and consumer products and combustion. Sunlight doesn't play the same role, it's a little different. So it's not quite the same as the field of outdoor atmospheric chemistry, which has been a big focus from of all, and for good reason, of all funding agencies over the past several decades. So given all that, my research group is focused on laboratory and field studies to investigate the physical properties of particulate matter. I run this research group at University of Colorado Boulder. Our goal is really to study emissions, transport, and fate of particulate matter, and sometimes gaseous components as well of air pollution in the indoor environment. And the idea is to produce knowledge and information that the public and decision makers can use to then make informed decisions to reduce people's exposure to particulate matter, with the ultimate goal, of course, to protect human health and the environment. So I chose to talk to you today about a couple of projects that are the ones that I'm probably most proud of helping lead so far. One is called HomeChem, House Observations of Microbial and Environmental Chemistry. And the second one is called CASA, Chemical Assessments of Surfaces and Air. So both of these were large collaborative indoor chemistry field campaign. What does that mean? That means that we go to a test house. You can see pictures of our test houses there. One is located at University of Texas at Austin. One is located at NIST in Maryland. What we did was we invited several research groups from all over the United States and Canada to bring their state-of-the-art instrumentation and to investigate science questions about the chemistry of indoor environments. The first project, HomeChem, was in 2018. We've focused on broader science questions about cooking, cleaning, activities that people do every day in their homes. And then for the second study, we tried to investigate the science questions that came up after, going through the data and publishing from the first study. We had more specific fundamental science questions with controlled additions of chemicals to the house. Things like what happens to wildfire smoke after it enters your home and interacts with the surfaces of your house? And then other air pollutants might come in and also interplay. So we're still working on data, still publishing paper from both of these studies, but I can tell you now with some confidence that I think that at least HomeChem, the first study, has been transformational in establishing what is considered now a new field in the chemistry of indoor environments. So today this is my last slide. I was tasked to talk to you a little bit about challenges. So talking about HomeChem and CASA is a good segue into this. So I'd say that I've been privileged so far to receive funding from more traditional sources like the US EPA and NSF, but those were single PI grants. And to be able to do this really large collaborative work, we actually were fortunate to receive funding from the Alfred P. Sloan Foundation. Their program on the chemistry of indoor environments, however, is ending this year. So that source no longer exists. One other thing that we're really missing in the field of indoor air quality is a deeper tie between aerosol science and engineering and environmental engineering research to health. There are no epidemiological studies done, for example, in indoor airs, in the indoor environment. And then other things about funding uncertainty, there have been some challenges recruiting talent for PhD studies, especially with the culture in graduate school changing a little bit after the pandemic. And the other issues are navigating 3-year funding cycles is very complicated because in science, in engineering specifically, the average time to complete a PhD is 5.5 years. So there's a mismatch there. And then, other issues that have already been mentioned, graduate student salary increases and inflation, making things a little bit trickier to manage these multi-year grants. With that, I would like to thank you for your attention.
Okay, Marina, thank you very much. That was an excellent presentation, and apologies again for the snafu with your slides.
No worries.
Next up, we're going to hear from Moweenot.
So hello, everyone. Thank you again for the opportunity. I am honored to be here today to talk to you about equitable medical imaging from the perspective of research in my lab, where we develop medical imaging systems. And we especially start with using theories, models, and simulations that we develop, such as this one, to design beamformers, which is a signal processing technique that really relies on the complex math and physics of sound propagation to determine how images will be created. We also design imaging probes like the one shown here, with the ultimate goal of using our designs to build and test prototypes that will improve ultrasound and photoacoustic image quality. Now, ultrasound and photoacoustic imaging systems generally use the same sensing hardware, so the software that's used to create images are typically interchangeable. So we can interface our designs with commercially available hardware like ultrasound systems, lasers, and robots to together create a new system that's the first of its kind to be tested on patients. This research is exciting because it allows us to consider all possible patients in our designs, and then we might learn something from our clinical studies that would require us to revisit our theories, models, and simulations, and the cycle of innovation continues from there. Zooming into the beamforming process for ultrasound and photoacoustic imaging, where in ultrasound we transmit sound that's reflected and then sensed by an array of sensors shown in gray. And in photoacoustic imaging, we instead transmit light that gets absorbed, and that absorption causes thermal expansion and the generation of sound wave that propagates to the sensors. Because there is a time of arrival difference between the location of the source and the sensor locations, we need to first align signals, and then we sum to get one signal that corresponds to the source that generated the recording. And we do this for multiple locations and multiple lines or beams in our image to create an image that way. Now, if we have a highly scattering environment, we might get a random signal on one of our channels that propagates and appears in that final image and causes what we call acoustic clutter that could make it difficult to distinguish the true signal from this artifact. One thing that we can do to address this clutter is to replace the summation operator with a cross-correlation operator. And we do that because signals that are similar to its neighbors will have a high spatial correlation or spatial coherence, whereas a signal correlated with the scatterer will have a very low spatial coherence. And this underlies the concept of coherence-based beamforming, which I invented as a graduate student initially for ultrasound imaging, with some example images shown here, starting with cardiac images. We have a lot of scattering in the chest wall region up here, which causes clutter, overriding the beating heart signal of interest. When we instead process the same data with the coherence-based approach, we can see the endocardial borders more clearly, which is important for diagnosing the cardiovascular health of an individual. And this is particularly important in improving the image quality in overweight or obese patients because the multiple tissue layers tend to generate more acoustic clutter. More recently, my lab has shown that we could use the same principle to distinguish fluid from solid masses, which may appear similarly dark in amplitude-based images. But when we take a spatial coherence approach, as shown on the bottom, we see that fluid masses have a lower spatial coherence relative to the surrounding tissue, whereas solid masses have similar spatial coherence. And as a result, we can use this to reduce the number of fluid breast masses, which are typically benign, yet may be unnecessarily recommended for biopsy because the content is unclear due to the presence of acoustic clutter. This is particularly promising for women with dense breast tissue who currently represent an underserved population with respect to medical imaging techniques to non-invasively detect breast cancer. When we transition to light transmission rather than sound transmission to get these photoacoustic images that I mentioned, we suffer from something all optics-based techniques suffer from, and that is optical penetration depth can be limited by melanin absorbers, which are increasingly common in darker-skinned individuals. Now, these melanin absorbers act as a photoacoustic sensor, and so what happens is we get a strong photoacoustic signal at the skin surface, and we also have a photoacoustic effect causing sound to scatter into the body that we want to image. And so this leads to an inherent skin tone bias with amplitude-based techniques that we can address with coherence-based beamforming as shown in the bottom row for all patients. And this is particularly promising for patients with darker skin tones who tend to suffer from more of the acoustic scattering that causes clutter. We are now looking to apply this concept to the emerging area of flexible array technology, which will allow us to conform to different body shapes and sizes for wearable health applications. However, this introduces the challenge of unknown array shapes, and you can appreciate the magnitude of this challenge when we try to make images with an incorrect array shape. So we're taking an approach where we say, what if we take guesses of the correct array shape, and we measure the spatial coherence and find out which array shape guess maximizes spatial coherence, and then use that as an indicator of the correct array shape, allowing us to make images like the one shown here, representing one of the first images obtained in my lab with this flexible array technology. And we're imaging a tooltip, and we got that image by attaching an optical fiber to the needle tool to allow us to visualize the tooltip for surgical and interventional guidance applications. In summary, I've shown you how a single signal processing technique enables us to have more equitable medical imaging. And more broadly, I've shown you how diversity drives innovation. This is not only diversity of thought, but also diversity of the data sets. If we're claiming to improve image quality, we want to make sure that our data upon which we're improving contains variations in all possible patients in our healthcare system. This also includes diversity of the personnel working on these problems, as represented by this sample of the current PhD students in my lab and the different degrees that they're pursuing in order to all have the same goal of this cycle of innovation research that I presented. This also includes the background diversity of the individuals in my lab, as represented with one example for myself as the lab director and the degrees that I have and the multiple department affiliations that I've had over the course of my career. So generally, I tend to ignore disciplinary silos when innovating these new ideas. I find them to be prohibitive, but I am very aware that I need to introduce these boundaries when writing grants and publishing papers in order to make the concepts more palatable to a particular community. I'll say thanks to my large team of students, postdocs, and collaborators who contributed and helped with various aspects of the work that I've presented. And of course, thanks to my funding sources to support this research. And thank you all for your attention.
Great. Well, thank you so much. We had 3 fantastic presentations here, and I'm sure there are going to be many questions from our PCAST members. And while people get their thoughts together, I will take the chair's prerogative and start out. So when we asked the 3 of you to speak, we asked you to mention things that are holding you back now. And you all seem so successful that it seems almost effortless. Okay, but that means it must be anything but. And so I'd ask each of you to maybe think about and address, were there particular challenges in pursuing the kind of interdisciplinary work that you're all involved in your careers, getting to the point where they are, okay, that maybe were different than, where you're at this particular time?
I can go first because an
Okay.
example just came to mind, if that's okay.
Sure.
I mentioned home chem and CASA, these studies that I'm incredibly proud of, and these were both funded by the Alfred P. Sloan Foundation. They're a fantastic program on the chemistry of indoor environments, which I think has lasted about 8 years. It's sunsetting now. And I just felt really privileged when I was invited to submit to that program by the then program manager, Dr. Paul Osuski. But I was a very early career faculty member just starting at CU, and I had been pitched as somebody who would aid the program in community building efforts. And my colleague Delphine Farmer, who is in the Department of Chemistry at Colorado State University, was also invited to lead the program's data management needs. So Delphine, I met with Delphine and I said, this is an incredible opportunity, and we're both very grateful. But we're also pre-tenure faculty members. And what really excites me, I have done so much community building. This is something I'm really passionate about, but my day job is to be a scientist. So together we pitched the idea that a field campaign would generate a data set for data management needs. And a field campaign would nurture the future graduate students of the program and would inherently generate community building. So we were able to pitch that to the program manager using a fair amount of creativity and rebudgeting to be able to make this study happen. So this isn't something that, was just readily available. We need to get really creative, and that's what it takes.
That's a great story. That's a great example of flexibility and figuring out new ways to get done what you want to get done. So let's see, William or Muinat?
Yes,
Either-
I have an example, and I think it's mostly centered around this concept of a departmental home. So as a faculty member, you are tied to one, maybe more departments. And I think, with me being so interdisciplinary in my background, I kind of struggled initially to figure out where do I fit in when I was applying to faculty positions to find that department that I thought was a good fit for me. And of course, the members of the department had to think the same about myself. And even now, as I've, made that decision, I think there's still some residual challenges because I do like to have the diversity of students in my lab, but it seems like each year different departments change their rules on how to, recruit the students, who's eligible, who's not. And that certainly does cause a downstream effect of challenges for me even today.
Mm-hmm. Okay. All right.
I would just add quickly, there's the funding challenges, which I do think foundations play a critical role in, as Marina was just highlighting, but also it's finding the right collaborators across fields, and how do you find the right people? We're all busy. Everyone's sort of stretched quite thin anyway. How do you find the right people who are willing to maybe step outside their comfort zone, write a grant together, or start a project together? And that kind of scouting the landscape and finding the right creative and sort of willing partners has been an interesting challenge.
How did you solve that challenge?
Well, I mean, I think some of it is meetings and going to finding the right kind of communities to join at meetings. Some of it was emailing people out of the blue and saying, hey, I've got a crazy idea about climate change and pollen seasons. Can we do a study together? And some of it has been just sort of pure random happenstance.
William, did you go to any conferences that are kind of more removed from your field to try to see who was there and, who might be a good collaborator?
I I have been to, I think the very broad conferences like the American Geophysical Union can be helpful, but really, this climate and health space is fascinating because it often falls between sort of fields and between funding agencies like NSF and NIH. And there I do think it's, I haven't been terribly successful at finding the right kind of broad interdisciplinary conferences for that.
Okay. All right. Well, we have several questions that have come up now, so let's move on to Bill Dolly.
Yeah, so I have two questions. One of them sort of broad, and the other one probably directed mostly at Mianat. So the first one is all of you have faced challenges with interdisciplinary science, and Mianat addressed some of those in talking about finding a departmental home. There are also a lot of challenges with funding, where funding panels tend to be biased toward whatever their own discipline is, and with publication, where publication review panels are similarly siloed. And I'm kind of curious how you've dealt with that. And then the question more directed toward Mianat is, how does funding for something that has such obvious practical applications as this coherence beamforming work out between industry and government? Is industry foresighted enough to fund the development of these new modalities, or is government funding needed to fill that gap?
So I'll go and address that question and your earlier questions. And I will say that the majority of the funding for the work that I presented is government funding. So that's whether that's the NSF or the NIH, those are the primary sources of government funding for me. However, foundation funding like the Alfred P. Sloan Foundation and even the Chan Zuckerberg Initiative has also been instrumental in filling this gap for me as well. And they've done it in a way that gives me greater flexibility than government funding to pursue some path that is not necessarily part of the government funding grant. And I like this funding because it touches on your earlier point as well, because, with me having such a broad background, what seems like an idea that would work to me may not necessarily be of this, like someone in a different one narrow area may not necessarily have that same thought. So when my proposals get to a review panel of someone who doesn't have the additional expertise to recognize how great of an idea this is, my proposal doesn't end up, faring very well. And so this is where the private foundations that give the flexibility really come in to allow this work to continue moving forward. And, regarding industry, I've tried, especially recently, to start interfacing more, because I do recognize that the only way that this technology is going to get to the patients of interest is if industry starts to get involved, whether that is partnering with existing companies or even starting commercial ventures of my own. So those are my thoughts on the questions that you raised.
Anybody
Do the
else?
other two want to comment on the interdisciplinary challenges?
I guess I would add, I think this is a good challenge to funding agencies to think outside the box, to team up together, that having joint calls between agencies is going to, I think, help quite a bit. And this is not just NSF and NIH. This extends to DOE, DOD, NASA, and other agencies. So I think this is where we need a whole of government and whole of science approach to do better on these interdisciplinary collaborations.
Yeah, in my field, it's definitely been an issue. Being an indoor air quality engineer, the vast majority of funding for air quality has gone to atmospheric chemistry, for good reason. But if you go to the NSF Directorate for Atmospheric Chemistry and you pitch an idea to study the indoor atmosphere, the answer has been known for decades. And finally, very, very slowly, it's starting to change. The pandemic definitely did a lot for that. People are finally starting to realize that this is where we spend our time. We should be studying it more. But I think we're still lacking productive collaborative research between health, chemistry, engineering, and the indoor environment. There's a great need, and it's still unmet.
Okay. All right, Sue Desmond-Hellman, you're next.
Thank you. I was just really struck by all three of the presentations, and I'd come work with you if you invited me, any of the three of you. Marina, you particularly talked about challenges of students coming and staying in your lab and working on your projects. And you said something that I wanted to hear more about, and that is the post-pandemic PhD. Can you help me understand what that is, and any of you, what the challenges are of attracting and keeping great folks to work on your projects, besides money, which I understand that.
Of course. Yeah. So what I mean is, I'm still early career. I've been at CU Boulder for 7 years now, so I can't speak for all the faculty, but I've been hearing somewhat broadly that, and in teaching, we noticed that the undergraduate community has really struggled during the pandemic, that online couple of years really changed the culture and affected a lot of skills negatively for a lot of undergraduate students that might be coming into graduate school very soon, and students that were close to graduation and are now into graduate school. I noticed a lot of issues with my students with interpersonal issues during group projects, for example, because they miss this pivotal moment in our undergrad engineering education where they're put into teams very early on. So then when I saw them when they were close to graduation, it was like, okay, you work in a team. Issues the entire semester. So it's because they had this deficiency that we didn't quite realize and had to address later. So now students coming into graduate school, we're noticing, and I think this has been a longer trend, but especially after the pandemic, I think cultural values have changed. What people want for their careers has changed. So a student wanting more of a 40-hour work week and not necessarily, thinking more broadly about research beyond what they need to do for their project to graduate, having that broader curiosity. Something happened there that we need to work as a society to help instill back, and maybe the others will agree or not, but that's been a little bit of my perception in engineering.
Yeah.
Yeah, I totally agree with a lot of the points that you've raised, Marina. And I would add that, what I've seen is that, with my research being interdisciplinary, I seek out specific skills that I think would be great for projects that I have in mind. And I can't hire everyone with the same skills. So what ends up happening is that each person in the lab has a unique skill, which could be great, but it could also make students feel isolated and really feel like they're in unfamiliar territory, to the point where there is a retention issue and they'd rather go back to something more familiar rather than this new thing that no one really knows what it is yet. Even I may not have all the answers because we're all figuring it out together.
Right. That's really helpful. This sense of catching up and what people missed during the pandemic is really coming through in what both of you say. So thank you.
Okay, Lisa Cooper.
So my question was actually quite similar, or sort of builds on this theme that you all are talking about. I think what I was trying to get at in my question is more along the lines of, how do we foster this kind of sort of cross-disciplinary, bigger picture thinking earlier, so that we have more people who are sort of curious and thinking this way? And how do we prepare people to work on these kinds of questions and in these kinds of environments earlier on in their training? And just wondering if you have any thoughts about that, what we do sort of maybe even at the K through 12 level or at the undergraduate level to start sort of foster the development of people who look more like you and are doing sort of this kind of cross and transdisciplinary work.
So I will say, I think that's a really tough one, because while we do want to get them excited about interdisciplinary research and work in general, you really do need the basic foundation and fundamentals to be strong in order to start combining things. And so I do think early on, it's really important to focus on building that strong foundation, but maybe give a taste of, this is what you can do if you have like an interest in multiple core foundations, maybe later on in the future, look toward this, but don't try to focus on it right now in such an early career stage.
Well, I think it would be helpful not to explain how you got into it. What was your pathway? How were you trained?
Yeah, that's a good question and good perspective. So I I always had an interest in healthcare challenges. And early on, K through 12, it was mostly science and math because that's all I knew. And it wasn't until I was in high school where I learned that I can combine science and math and do this thing called engineering. And from there, I, went to MIT for my undergrad in engineering. And even though I always had an interest in healthcare and I knew I wanted to do something related to biomedical engineering in the future, I liked the mechanical engineering curriculum at MIT, and not to mention MIT didn't have a major in biomedical engineering, so I minored in it. But I thought it was really important for me to get that engineering foundation through a discipline that I could identify with and that I had liked. And then I went on to get my PhD in biomedical engineering. And from there, that's when, I started adding on, initially my PhD was in the ultrasound world, purely ultrasound. And when I did my postdoc, I added on the optics, the robotics, the computer science components. And then when I started my lab, that was a really wide open playground to kind of start combining all these other different ideas, building on the core principles that I had at each step of the way.
So Marina, did you have strong supportive mentoring? I mean, it kind of sounds like there must have been people who were encouraging you that this would be okay.
Yeah, I definitely had supportive mentors at each step of the way, but it wasn't necessarily, for, one mentor that got me all the way through where I am. It was one, at each step of the way, someone recognized the talents and the potential and suggested things to me, like pursuing graduate school. That wasn't initially on my radar. Even becoming a professor, my graduate advisor said, "Oh, I think you should try that as a career. It looks like you have what it takes to succeed." And prior to him even saying that, I'd never considered a career in academia.
Maybe Marina and Bill would like, and William would like to
chime in.
Yeah.
I think I'm so excited to hear you share your story because I feel like I'm a very transdisciplinary scientist myself, and just navigating that space and trying to find people to mentor you on one thing or the other and trying to kind of connect these people across different fields has been challenging. And I just wondered whether if people could learn earlier about the fact that there are all these things that are out there that are connected to each other, that it might, sort of help them figure out the path more easily. But Marina and William, any other thoughts?
Thank you, Moinat, for sharing your story. I think that's really impressive. I won't bore you with mine, but I think answering the question about trying to foster this in the students today and in the graduate students specifically, I think one interesting idea could be to add more teamwork, but more interdisciplinary teamwork to the undergrad and the graduate at the undergrad and graduate level, where each team member actually has their own specialty. Because I completely agree with what Moinat said. We can't just go do collaborative work if you don't own your own science, right? You need to be able to do that. And then you branch out and have the curiosity to understand the other fields. And then you know where you can really contribute by linking them together. You can't do one without the other. So we can foster that in our undergraduate student education, graduate student education with more teamwork and rotations, but without losing sight that they really need foundational knowledge first.
William?
Yeah, I agree completely. And I would only add that I think there's an opportunity in our undergraduate curriculum to build systems level thinking and how to talk to experts in other disciplines into the classes themselves. And that can be through project-based classes, research-based classes, and, sort of interdisciplinary fellowships or summer internships for undergrads as well. And we've been launching a new Earth and Environmental Science major here at the University of Utah and trying to think through how to incorporate that systems level thinking, where maybe you go deep in a specific area of the Earth system, but you understand and can talk to other scientists in other areas.
Maria, if I could jump in just with one build up on this, I'm curious to hear from each of our discussants, and thank you all very much for your very impressive presentations. I'm dazzled by your work. How much project-based or research-based undergraduate training did each of you get? And what would you say the potential role of that in fostering what we've been talking about could be?
a lot on my end. Certainly, I would say I received a lot of different research training as an undergrad, and that was also instrumental in deciding I wanted to be a scientist. And so I think it should play an important role from my perspective.
Yeah, absolutely. My case is a little different. I did my undergrad and master's degrees in Brazil. I'm originally from Brazil. I only came to the United States for my PhD. So during my undergrad career, I did a year of research and as an undergraduate researcher. And my last semester, everybody has to do an internship, and mine was at a university in Canada. So I was also doing research for that. So then I knew I wanted to be a professor by the time I finished.
Yes, and for me, I did research as an undergrad on the side. I was a mechanical engineer, but I did research with someone in the material science department. So that was actually pivotal for just being exposed to another discipline and how things work in that field. And later did contribute to some of my way of thinking even now. And then in my mechanical engineering curriculum, a lot of the more like higher level courses are very hands-on. You build things, you make products, you showcase the products, you compete your designs someone else. The robot competition is really popular, and so I did get a lot of hands-on experience, but that was more using the fundamental mechanical engineering principles and not necessarily helping me to cross disciplines at that stage with those type of projects.
Thank you very much. Thank you for the interjection, Maria.
Yeah. Let's see, let's go to Paula Hammond.
I was really impressed with each of you, and I think you represent the future in so many ways. I think the fact that you are interdisciplinary and you're also staking out new ground makes what you do extremely exciting. But I'm wondering how you are supported as young faculty. Can you talk a little bit about your mentored experience as faculty members and what kinds of things might enhance that experience as you kind of see your journey moving forward, even as you move into mid-career? How are you supported as someone who works at these interfaces? And what are some of the challenges that you might face? Because I imagine you are at a frontier, you're expected perhaps to be present in more than one community at the same time.
Well, I'd say that I feel pretty privileged to have had a good network of mentors. I think one thing too that I think not every early career faculty member realizes that is what you need is not one mentor or two, is really a network. And then you pick and choose what you want to actually listen from each of them. And, they can tell you 10 things, but we're really just looking for the 2 or 3 that you're going to take home with you. And I think I felt lucky to realize that early on and to have had a network of mentors, both at CU Boulder and in the fields of indoor quality and environmental engineering, and to be well connected with older female faculty who are much farther than I am, to be able to tell me how it was for them. And it's been really insightful. So I feel really privileged. I hope that others are able to get what I've been lucky to have.
Yeah, and I'll jump in and add that, I think I, had very strong mentoring, especially pre-tenure, where we had a formal, mentor assignment, someone in the department, someone outside of the department, but then that stopped for me, at least at the tenure level, now that I'm tenured. And I do find it kind of tough to navigate new ground after tenure, because I think what I realize is that everybody's path is different now. And so while, as a junior faculty or as a pre-tenured faculty, majority of my cohort are all striving for the same thing in the sense of, getting promoted to associate professor. And a lot of the check marks are the same, like the NSF Career Award, for example. So we have a strong cohort. But now I find that I'm more of, kind of charting my own territory, and they're not, similar milestones, even among the people that I came in with. And so things like, I want to grow my lab. how do I get more space? Like, it's been really challenging to figure this out, and would love, advice if there is any among you all. And aside from that, I do agree that there are challenges, with the multiple affiliations that I have both on campus at the university and in my multiple communities. And, it's really tough to say no, because I do want to do everything. I would love to do everything, but my time is limited and I just physically cannot do everything. And so it's great when I have understanding people who've asked and I have to turn down. And it's not so great when there is no understanding. And then it's like, well, I'm sorry, I really can't do this. And so it does put an additional pressure and burden that, makes it difficult to operate in doing the research that I love and that I want to do.
Okay. William, anything on this one?
I completely agree with what everyone was just saying. I've been really fortunate to have a wonderful group of mentors at my university and around the country. And to me, it seems like, like you were saying, Muinat, it really, once you hit tenure, and then it opens up a lot, and then understanding where you want to go and how to get there is a much harder path to walk. And really getting the advice on how to allocate your time among really competing interests and competing possibilities has been, I don't know what the solutions are there, but that's been something I've hit many times.
Great. Okay, Vicky Sato.
Like many others, thank you for the work that you're doing. I'm energized by it, and I'm energized by your entrepreneurial spirit in creating paths that are unique. It's really great to hear. We've heard some positive things about the kinds of encouragement and mentoring you've gotten, but I'm also curious about the other side. As you were building these unusual synthetic, collaborative, transdisciplinary careers, did you get specific and pointed negative feedback about the fact that bridging these disciplines was not the way to get tenure, that people won't be able to judge your specialty because, hey, do you have a specialty? And how can we tell what's really your work as opposed to the work of the team? So could you comment at all about whether there are negative forces at play and how you process that information?
Yeah, of course there are negative forces at play. Yes,
I'm shocked.
a lot of them coming from inside me. Yeah, imposter syndrome is a big thing. I will add that. And I will say, the two examples I chose to talk about today, home chem, we were able to get that funded very early on and during my tenure track career, and I felt lots of pressure, internally motivated and externally motivated to what's the next big thing? What is going to be the thing that actually sets me apart? Because if that's the only major grant, I was really concerned that I wouldn't be seen very seriously as a researcher on my own, but I would just be seen as a connector. And particularly for me, with somebody with an environmental engineering background, to work with these highly distinguished atmospheric chemists, who is a community and a niche in itself, is quite humbling, and it can be nerve-wracking. So for me, it was very important to secure additional single PI funding. So I was able to get the NSF Career, the EPA STAR, and that was really trying to establish myself on my own and have my own understanding of my own science that is complementary to what the atmospheric chemists are doing, without trying to myself become a lesser atmospheric chemist, by collaborating with them. So yes, it's a challenge. My answer is not as broadly applicable as just my example, but yeah, that's how I felt pressure for sure to also establish my own stake, I guess, in the field.
Marina, do you collaborate with people in building technology programs?
So I've had collaborators, and as we speak, I am currently in Hawaii at a hotel room. I am in the Indoor Air Conference. Indoor Air Conference is about environmental quality, air quality, building science. So yes, there are 900 people in the building next door meeting, and there are several building scientists and indoor air quality engineers and some chemists as well that we've brought into the field in the past few years. So we collaborate. I don't have any specific research projects with building scientists right now, but it's something that I've been working on, and we've submitted proposals. But yeah, it's an active area of collaboration for sure, especially as you think about the building of the future, something so important, right? With technology advancing everywhere, we carry computers in our pockets and we have Internet of Things. But our buildings are still not designed to provide adequate air quality. It's just not part of the process, and all this technological development, we're still needing that little piece. So yeah, very important.
Yeah, well, it seems like at least, you know, if anything positive came out of the pandemic, the awareness of great indoor air quality, I think, has come to the forefront. So maybe hope is on the way.
Absolutely.
Anybody else? Does anybody else want to address that?
Yes, I can chime in really quickly and say, yes, I've heard all of, what you said about the possible negative feedback. I've heard it all. Needing to be known in one area, don't spread myself too thin. So my approach was to create a new name for my area. And I said, well, I am in one area. It's called this. Like I'm doing photoacoustic guided surgery. That is the area. It combines optics, acoustics, and robotics, but it's one area. So that's one thing that I did differently to kind of address those concerns. I've heard that in some cases, it's negative feedback where it was too early to apply for some of the awards that I ended up winning. I just applied anyway. I figured, let the committee decide. That's not, for me to count myself out. And a lot of negativity surrounding kind of getting my first R01 grant from the NIH. System. I didn't know how the scores worked out, what translated to a fundable score or not. And I did get some negative feedback. Oh, when sharing my scores and immediately being told, oh, that's not going to get funded. That while it was true, like that score wasn't funded, it was kind of very harsh feedback for someone new and interested and invigorated and trying to, do everything that I can to get something funded. And even just when it was, time to address those reviews, I was told to, just address the reviews, but it's not always simple to just address the reviews. Sometimes the reviewers are wrong. Sometimes there's a lot of bias in the reviews. When I compare my reviews to others, like I seem to be reviewed more harshly in some cases. So, some of the just address the reviews advice wasn't very helpful for me.
I would add also just that this tension between collaborative funding and solo PI funding that Marina mentioned, I thought strategically about that. The first grant I was a part of was a collaborative grant, and I made the time to go after individual grants to have a solo PI grant or two before going up for tenure. And that's something that I know a lot of junior faculty and that I cross paths with struggle with a lot, is they want to do team science and want to do collaborative projects, but to be legible, it often takes some solo funding as well. And that's a tension. I feel fortunate that my colleagues don't at all. I felt no pressure that you aren't enough of a biologist to get tenure in a biology department, that they were very recognizing of this is important research and valuable.
Thank you.
Great, thanks. Great answers. Let's see, Andrea Goldsmith, you're up next.
Thanks so much for the great discussion. I guess the question I have, I'm wearing my Dean of Engineering hat right now, and it's how do we educate students differently, if at all, to participate in interdisciplinary research? And similarly, how should universities be thinking about supporting faculty that want to do interdisciplinary research? You mentioned things about the tenure process. Often you need to forge interdisciplinary collaborations before you go out for a big grant, for example. And so what are the things that we should be thinking about within universities that might need to change as interdisciplinary research becomes much bigger part of advancing the state of the art in research in general, in engineering and related fields?
Well, for me, the first thing that comes to mind is the role of centers, at least at Hopkins. I don't know how it is at other institutions, but centers are designed to bring together faculty, students from different departments to work on a common goal or theme that truly is interdisciplinary. And I think overall it's a great idea, but then when, me as one individual is affiliated with multiple centers, then that becomes very difficult to navigate.
I agree about centers entirely. And also I think that, changing how things are evaluated and credited in the RPT tenure promotion process, that it's very clear and transparent how collaborative research is evaluated, and the incentive structures, right? That having seed grants that incentivize collaborations, having ways to build bridges and meet the people either at your university or at other universities that are the great collaborators for that work. Those have been some of the challenges that I've faced, and I think is how we could better set up the system.
Yeah, I don't have much more to add. I think centers from the higher level, seed funding from the lower level are both things that are really important in helping foster these collaborations, especially early on, because it's very difficult to find the right collaborator, figure out where even an interdisciplinary approach could get funding. It takes time, it takes a lot of time. So without seed funding to foster that, it doesn't come to fruition. It's impossible. The activation energy is too high. In terms of education, I'll add though, I'm an environmental engineer in a mechanical engineering department. So I'm always, learning about things that they are doing as mechanical engineers. And I think it's so cool how many projects, project-based learning, classes there are, both at the undergrad and the graduate and the graduate level, especially when there are companies involved coming from the outside. If there's a company involved and they have a specific project they need addressed, then ideally you can find students from multiple departments to work together and solve that problem. And there you have it, interdisciplinary collaboration at the undergraduate level. So I think that industry has a good potential for innovation there at the undergraduate and at graduate level, not just getting the answers to their questions, but also instilling that entrepreneurial and interdisciplinary collaborative culture into the next generation.
If I could just, go ahead, sorry.
Oh, I just wanted to riff on that a little bit, in that I think that's something centers can do as well. So something that the center that I direct, the Wilkes Center, does is run hackathons that are 24-hour problem, and you don't have to have coding experience, but they're intense problem solving challenges that the goal is to bring students, both undergrad and grad, from across campus to tackle an important problem like wildfire in the West. And so I think there's opportunities both in classes and sort of across campus through centers to get students from different disciplines working together. And we have cash prizes as the main way we incentivize students to show up: free food and cash prizes.
I mean, so I just wanted to follow up that universities have always been structured according to disciplines, and then centers and institutes are kind of the T that crosses them. But there's challenges in a center or an institute hiring a faculty member who needs to have a home department. There's challenges in teaching interdisciplinary, in recruiting graduate students that are interdisciplinary. So I'm just wondering if any of you have thoughts about, should we be thinking about changing structures of universities? For example, Stanford just started a School of Sustainability, which is an interdisciplinary school, very different from traditional schools. Any thoughts about that, particularly on the education front? Because I think that you touched on the research front with the centers and institutes.
So my thoughts on that is, I think that's kind of the role of like majors and minors or double majors. But I think if, we see either within our own universities or across the nation, a trend of majority of students are choosing to double major in the same two majors, or choosing a major and a minor in the same areas, then that does speak to a role for maybe it's time to rethink the overlap between these areas and start a new discipline based on that.
I think regarding the environment, there's a huge role for structural changes at our universities. The disciplines of the 20th century or 19th century are really poorly set up to tackle environmental challenges of the 21st century. And so whether this is new schools of earth and environment or climate or sustainability and how you want to bring different groups in, you have social sciences, engineering, humanities. I think there's a lot of questions to figure out how to do that well, but we've got to be thinking more creatively around the structures because you collaborate with the people that you see and cross paths with, and you're evaluated by as well. So that's a key challenge.
Yeah, and I want to also add, I think there's also a role for, like, if you have already a biomedical engineering department at your school, for example, and they're used to the traditional way of doing things, I think there's certainly a role for creating, okay, that's old BME, this is new BME. They both exist at the same school. The new BME does things a little differently, but it's kind of, you know, another way that I would say it's kind of a more provocative idea to address the challenge of people wanting to stay in the same, like, historical way of thinking. Yeah, I struggle with coming up with novel solutions for the way universities are run because things move at such glacial pace. And now with the financial stresses that most of the universities are going through post-pandemic, it's difficult to even start brainstorming on how to shake the status quo. It's when they're barely hanging on as they are, you know, I don't want to mess with it too much. But yeah, I would say that even within our College of Engineering, we have the traditional disciplines, but then environmental engineering is considered a college level program. Biomedical is a college level program, material science as well. So I think there's room for creating these other fields. And then if it becomes big enough, then we make it into a department. But the whole administrative structure and the way we divide the credits and the teaching credits and the TA assignments between the programs and the departments is super challenging, and there's no right solution. So I just have more complaints and no solution for you. Sorry.
Well, they're hard problems, Marina. Steve Pacala.
So the only danger in inviting three people like you to address us is that we could falsely conclude that there is absolutely nothing wrong with the nation's capacity to produce interdisciplinary researchers. So it was really a hoot to hear you all. Each one of you, I think, well, two of three, I'm sure, but I think all three of you mentioned the critical role of private philanthropy in your careers, right? And what I want to know is two things. First, what specifically about the private philanthropy was pivotal? Was it the capacity to convince just a single person who was the contact person that you wanted to do something new? So was it flexibility, or was it the low red tape? I mean, what was it that was special about that? Because, you know, we've tried a bunch of different programs. Bill, you just mentioned some of them that the federal government has tried to do to improve, to promote this sort of thing, and yet you all singled out private philanthropy. So I'd like to know what we could do as a nation, right? Should we be somehow subsidizing private philanthropy because they just do a better job of this than we do, or what, right?
I guess I would say from my perspective, it's the ability to take risks, and that does come down to this flexibility that you know, when you write a grant is a very narrow set of what you can do in the world of possibilities. And sitting back and thinking creatively, what would you do if you had the resources and the flexibility? What societal problems would you tackle is a very different question than what can I get funded from NIH or NSF. And so for me, there was really that sort of flexibility and risk taking and the ability to think outside disciplines as well too, right? That we're going to fund a bunch of social scientists to come work with us on this. And that's possible with philanthropy and much harder with government funding.
Yeah, I think the flexibility is far greater. For me, the Sloan Foundation funding was transformative in that I was able to be put into the same room as these very, you know, established scientists that were there because they were invited by the Alfred P. Sloan Foundation. So it created opportunities for me that I wouldn't have been able to cold call these people and say, hey, let's establish an NSF center together. I was not at that stage. They had not heard of me, but because I was invited to be in the same room with them by the Alfred P. Sloan Foundation, all of a sudden I get a little bit more clout. So there is that role. I'm not going to deny that exists. On the other hand, the federal funding agencies are very mission focused, right? EPA calls are very, very targeted. Which is fantastic. I think they're trying to address a need. I'm not going to criticize it too much, but there also needs to be more flexible, creative opportunities if you really want to do something transformative and create new fields and create collaborations that didn't exist before. NSF centers are fantastic. They are hard to come by. They're very, very competitive, very difficult, and they are also very mission focused. We pitch health related stuff to NSF. They'll say, go to NIH. You pitch it to NIH and they say, no, that's engineering, go to NSF. We need more flexible, I guess, opportunities for these collaborations.
Yeah, I echo this theme of flexibility. That's certainly what is, at least for me, and it sounds like my co-panelists, most attractive about these private philanthropy. And I will say that, the government does have some element of this. Like, I just won the Waterman Award this year, and that is an amazing source of flexibility for me, like that I've never experienced with government funding. So to answer the second part of the question as to what could the government do, give out more of these awards, not necessarily, the Waterman Award, but the same concept where you just get an award, you just get X amount of dollars because you've already done something, substantial and great, and here, do something else. And I think, that could be another way to kind of parallel what we find as the value of these private philanthropy. So just an allocation of X dollars. And I think Canada does something like this too, where, I've been tapped for, exploring faculty careers there. And one of the first things they made it clear to tell me is that in Canada, you don't have to work so hard to write grants. Like, we just give everybody money to do research. So yeah, that's an idea.
Wow.
But rather than for the federal government to somehow fund a consortium of private philanthropies who do have a track record already in doing it. Sue Desmond-Hellmann, is that even legal? I mean, she ran the Microsoft or the Gates Foundation.
It is definitely legal. It is to this day unusual for two foundations, two philanthropies to collaborate together or pool money, but it's not unheard of. For big global health issues, it's quite common.
Yeah, and there have been collaborations between federal agencies and foundations. So that has
definitely CDC, NIH, WHO. I mean, a really good example to look at is getting rid of polio. That's definitely a big global collaboration.
But that is mission focused. I mean, what we'd be talking about here is somehow an innovation fund, right?
Yeah, and a different example that's more to an innovation fund like style would be focusing on mRNA. Could the world benefit from mRNA vaccines? Again, it's slightly directed. It's not as basic, but also quite broad and more research oriented.
Yeah, another example is that the Simons Foundation co-funds projects with NSF of various sorts. I don't think the money actually moves between those two entities. I think it goes from each to their selected fundees.
Yeah. Okay. All right. Lisa Cooper, you've got the last question because we need to close this session out. Okay.
Sure. It's actually not a question. I'm just putting a plug in for the Bloomberg Distinguished Professors Program at Johns Hopkins, because it does exactly what you all have been talking about in terms of private philanthropy, funding people who are doing transdisciplinary work, and funding a whole sort of cohort or cadre of people, and then encouraging them to collaborate with one another. And now it's even like gone on to like bringing together like cluster hires to work on, in a certain space where transdisciplinary science is required. So I think that's a great model. Just a plug for that.
Okay. So William, Marina, it's been just a fabulous session, and we have benefited immensely from hearing about your research results, from your personal experiences, and your thoughts about how to keep interdisciplinary science strong and even expand it. So we thank you so much for your participation and the time that you took to spend with us today. So so we need to move on, and I'd like to let everyone know that please take a look at PCAST's latest announcement on our website. There was going to be a workshop on safeguarding America's groundwater security that's going to be taking place in Arizona on Monday, July 22nd. For more details and or to request to participate, email our PCAST staff no later than Tuesday, July 16th, which is next week. So I'd like to reiterate here that a recording of this event, the bios and any presented material will be available on the PCAST website next week. Let me ask my co-chair, Frances Arnold, if she has any closing comments.
Just want to thank 3 wonderful speakers sharing your experiences with us and with the public, and thank all the PCAST members, and thank you to the public who joined in with us.
Okay, thank you.
I wish you all the best in your future careers.
Thank you for having us.
Yep.
Thank you.
Right.
So much.
Okay, and that concludes this public session of PCAST.